The next speaker is Paul Duuring, a senior geologist in the Mineral Systems Group. Paul today is giving a talk on a topic that is related to a collaborative project he was involved with SEPA Resources.
Thanks, Klaus. Today I'm going to give a very short progress update on work that I'm doing in collaboration with SEPA Resources and CoreScan, and I'm looking at the style of mineralization at the Obelisk deposit. So where is Obelisk located? On the diagram up here, the North Paterson area is located on the eastern margin of the Pilbara Craton. What's special about Obelisk, which you can see in these red triangles, is that it's hosted in Proterozoic basement rock. So you can see by the green Canning Basin sediment draped over the obelisk is essentially a blind deposit. And to make matters worse, there's up to 70 metres of transported material on top of the Canning Basin. So it's a very big challenge to try to explore in this area. If we zoom in on this area and look at a solid geology interpretation, and that's pretty much with the Canning Basin removed, this is an image of Adam Baths, you can see that the target area is denominated by the location of the drill holes there. And so mineralization at Obelisk is located at the contact between the Proterozoic amphibolite in green and the adjacent metasedimentary rocks in yellow, both of which are sandwiched between a sea of felsic granites. So the topic of my talk today is quite simple. I'm trying to really unravel what is the source of the fluids. And the hypothesis is that felsic magmatism is the source of fluids and metals at Obelisk. To do so, I'm just going to whiz through some of the methodology that I've employed so far. First of all, SEPA Resources has provided 5 drill holes, 2 of which are permanently available for the public to view at the Perth Core Library, one of which was a EIS hole, the other one was donated by SEPA Resources. All 5 drill holes have been scanned by the GSWA high logger, and one of these drill holes has been scanned by CoreScan free of charge, and that data will be made available to the public shortly. And so those scanning methods, they complement each other. The GSWA high logger provides a 8mm scan down the centre of the drill core, whereas the CoreScan provides 80% coverage, spatial coverage of the drill core. The high logger has thermal infrared, whereas the CoreScan doesn't. And I use both of them to map out alteration minerals and also to elucidate what the protoliths are likely to be. I employed petrological studies, thin section and whole rock geochemical analyses to work out the protoliths, but also to look at their alteration variants. Fluid inclusions was a blind alley for me. I was very hopeful at the very beginning because these quartz veins were beautiful extensional growth fabrics. However, I think it's because the obelisk is wedged between the felsic granites, these quartz veins have been thermally recrystallized. So unfortunately, these fluid inclusions, which would be very handy to use to identify fluid sources, unfortunately that wasn't available to me. Instead, I've been looking mostly at TEMA images, which are BAC's SEM images, which I can then look at a mineral map to look at alteration minerals and hopefully identify minerals which are possible to date. So thereby constraining the age of the protoliths, but also the alteration minerals. So I'm now going to talk a little bit about the rock types before I head towards alteration. So on the slide here, I have the geology interpretation of the 5 drill holes. And on the y-axis, I have, on the y-axis, I have depth increasing down the drill hole, and I'm just going to talk to this drill hole number 2. The oldest drill rock type is a metasemite, and you can see a photograph here. It's got that nice granular texture of a metamorphosed sandstone. That is intruded by an amphibolite, shown here, And both of them have been folded by regional folding and therefore resulting in an axial planar fabric, which you can see by the yellow line. The mineralization is indicated by red and blue graphs. The red is the gold, the blue is the copper. And you can see that the mineralization is at the contact between those two rock types. There is a post-mineralization dolerite dike indicated by the purple, and that cuts those existing rock types and also cuts mineralization and doesn't have that foliation. And that in turn is cut by felsic pegmatites, which is post-mineralization, it post-dates copper-gold mineralization. There are two stages of alteration. The first stage is the main stage and results in copper-gold mineralization. And here I show an example of metasamite. The drill core, this is a petrophysic plug which has been drilled out and then placed back. And you can see the core scan data draped over the drill core. And this is an example of metasamite, and there's an extensional quartz vein with margins here and there with some chalcopyrite. Shows beautiful extensional growth fabrics at right angles to the quartz vein. And in this example, it is surrounded by biotite amphibole alteration. And by coincidence, in this example, you can see the later stage chlorite alteration partly replacing the alteration zone. To put that in some kind of a timing context, I've got a cartoon here. And this shows the extensional quartz vein in yellow with a alteration halo in brown. And you can see that it's mostly located at the contact between the amphibolite and the metasamite. And the quartz vein cuts the axial planar fabric. These veins have been sheared, so unfortunately that was the part of the culprit for destroying my fluid inclusions. And then it's cut by that post-mineralization dolerite dike. Which leads me to the later stage alteration, which is shown here by the occurrence of the pegmatite. And that has beautiful timing relationships in the drill core where it clearly cuts the dolerite and the earlier stage, the quartz vein. This event has been dated by Rob Creaser, University of Alberta, and what we have here in this photograph is that's entirely the pegmatite. It's been cut by a narrow veinlet of quartz with white mica and molybdenite. And rhenium-osmium dating of the molybdenite gives an age of about 652 MA, which overlaps closely with the age of felsic magmatism in the area. The Venus deposit has been dated, and that's a published date for felsic magmatism. We've also dated the granitic pegmatite at Obelisk, but it's still preliminary, but I can say that it overlaps that age. So there is a co-temporal relationship between molybdenum mineralization and felsic magmatism. And I have some relative timing relationships with chalcopyrite, pyrrhotite alteration. In this photograph here, this mineralizing event does cut the earlier quartz vein. So even though I haven't dated this in a relative sense, it overlaps, I believe, this timing of the molybdenum event. So I'm just going to remind you what I've shown you, and I've sort of harped about this a little bit in terms of going through these discrete episodes. I've shown you this slide here, which I'm quite confident that there's at least a co-temporal relationship between felsic magmatism and molybdenum mineralization. I am interested in the age and the source of the fluids for the earlier events. Is it related to felsic magmatism? But what I'm quite confident about is that there are these intervening geological events. So I think what we're not dealing with is just an earlier episodes of the felsic magmatism, evolution of a fluid. I think there's actually some discrete geological events separating these two mineralizing events at Obelisk. So what I've been trying to do the last 6 months is trying to really constrain the source of that fluid, initially by dating, then leading towards tracing the fluid source. Tried in situ dating of alteration. Biotite is part of that alteration mineral assemblage. Rubidium strontium analysis of the biotite. Also trying to date the timing of phosphates which are parallel to that axial planar fabric. So that last attempt is pretty much putting an age bracket on the mineralising events. Unfortunately, what I've basically seen is we're seeing these ages stacked on top of each other, when in fact some of these older events really are giving younger events than the molybdenite age, which to me I think it's most logical that either these dates are being reset or we've got precipitation, reprecipitation of phosphates, so that now they have the hallmarks of the later alteration events. So I've put a lot of my hope on dating to try to work out the timing of these events and the source of the fluids, but now I'll turn my focus towards looking at mineral chemistry, isotope studies. So mineral chemistry, I'd be interested in rutile, titanite, apatite, all of which are part of the both alteration assemblages. Isotopes, not exactly sure, maybe lead isotopes, if I could characterise the lead isotopic signature of the sulfides and then relate them to the K-felspar lead isotope signature of nearby felsic intrusions. So the conclusion of this talk is that felsic magmatism is the source of fluids and metals, with the caveat that I'm really talking about the late stage alteration where I have that supporting age information, but it's still unclear whether the main stage is related to felsic magmatism, its true age, and I'll be focusing my efforts on that. Thank you.